And when I think about the pace of change here, I'm reminded of this quote from Bill when he talks about how we sometimes tend to overestimate what we can do in the short run, but underestimate what we can do in the long run. And the progress we have made with AI and MR are just amazing. In fact, when I think about the compute power, Craig Mundy, who happens to be a former CTO of Microsoft, was telling me how the first set of supercomputers that he was very much part of were built using just 13,000 transistors. And the Xbox One X has 7 billion transistors. And so we've come a long way in terms of creating this abundance of compute power. But yet, we still have many unsolved problems, unsolved computational problems. I mean, just take the challenge of energy. What if we could discover that new material, that new superconducting material that could enable us to have lossless power transmission? That could be the answer to our energy challenge. What if we could tackle global warming by discovering that catalyst that could absorb carbon? What if we could tackle the challenge of food production by figuring out, in fact, how natural enzymes work? In fact, here we are in 2017 and we can't, in fact, model these natural enzymes so that we can then figure out what artificial catalysts can mimic it. Take medicine. We talk about precision medicine, but in order to be able to really make sure that precision medicine has the efficacy, you need to be able to model the drug interactions. Again, an unsolved problem. It's these unsolved problems, computational problems, that were the inspiration. Over 10 years ago, when, in fact, Craig Mundy and a team at Microsoft got started on this journey to build a quantum computer. You know, we set out with a goal of not just trying to achieve a few scientific milestones, but we sort of went back to the very core first principles and said, what would it take to build a truly scalable quantum computer? And the intuition behind the power of a quantum computer is best understood, perhaps, by thinking about and visualizing the limitations of a classical computer. Take the corn maze, and if you said, let's try and solve this. You know, the way the classical computer would try and tackle this is to start, trace a path, hit an obstacle, retrace, trace another path, retrace, trace another path, retrace. So it's this brute force mechanism because we are captive to the one human machine. But a quantum computer changes it. Quantum computer enables you to encode information, not just as 1 or 0, but as 1 and 0 simultaneously. That means it unlocks amazing parallelism. So you saw that. You could take a quantum computer and solve some of these unsolvable problems because they approach it with that amazing parallelism where they'll take every path in the corn maze simultaneously. That's the intuition behind the power of quantum. Of course, building a quantum computer requires a lot more than just that simple intuition. We've had to assemble a world-class team. In fact, we've had to take a very novel approach of bringing together breakthroughs in math, fundamental physics, and computer science together. And put a system, or get started on a journey to put a system that's going to be a truly scalable, general-purpose quantum computer. And to help give you a bit more insight into this journey that we are on, I wanted to invite up on stage a few of my friends. Dr. Michael Friedman, who is a Fields Medal winner in mathematics, Dr. Charlie Marcus and Dr. Leo Cohen-Haven, who are two physicists, and Dr. Krista Savore, who is a computer scientist. Please help me welcome all of them on stage.
Hi, sir.
Charlie? Yeah.
Satya.
Mike? All right. So Mike, let's start with math. I know one of the foundational things to our quantum approach is this topological qubit.
Yeah.
Give us a little bit of intuition behind that.
Sure, well, let's start with the first word, topology. Topology is the study of those properties of shapes which don't change when you deform them. So a basic example would be if you imagine a loop of string in space. It could be a simple loop, almost like a circle, or deformed a little bit, or it could be more complicated and tied in a knot some way. And it's a global property. The information of whether it's a knot or an unknot can't be observed by looking at small segments. You have to step back and see the global picture. Now, Microsoft's qubit will be based on a new form of matter called topological matter that also has this property that the information stored in the matter is stored globally. You can't find the information in any particular place. Now, how does that work? Well, it's based on an idea called electron fractionalization. The basic information is the electron there or not there is fractionalized and it's spread out. That information about the electron is broken into two Majorana particles, and they're physically separated in the material. And the fact that this basic property of being there is nowhere in particular but spread out makes it nearly impossible for the environment to interact with the electron.
It's pretty amazing. I mean,
it protects it.
Yeah, I mean, just the fact that information can be coded into essentially these knots, but you can't observe it locally, but you can see it globally, is pretty stunning. But you had said something to me which I had not understood when I was learning math, I guess, is that this has something to do with square roots.
It does. Deeply. The Dirac equation, which describes the electron, is the square root of, it's called the Klein-Gordon equation. It's a relativistic wave equation. And when you take its square root, you find a special form of Schrodinger's equation. Do you remember that cat?
Yeah, the cat, yeah.
Which is perfect for describing electrons. It's an amazing thing in math and engineering and physics that the square root is almost always more powerful than the original object. So many people in the audience will have worked with I, the square root of -1. And really, I does just about everything in engineering. Interference, impedance, dissipation.
So it's not imaginary.
It's not imaginary. I is engineering. And we're working with a different square root, but just as important to one.
That's so awesome. So Leo, now, if you take that math foundation, the topological qubit and the topological matter, ultimately, though, we've got to instantiate it in some physical way. How are we going about that?
Well, luckily, Mike and his collaborators also came up with some specific proposals on what to do in order to observe these Majoranas. And the idea is that you have to construct an electronic device with some carefully designed materials that do include semiconductors, but also superconductors. And if you cool this electronic chip down to very, very low temperatures, then one should be able to observe these Majoranas. And I'm an experimentalist, a physicist, and we picked up this idea and were able to report the first proof of Majoranas back in 2012. And the Majoranas are really important for us because they are in fact quantum superpositions of simultaneously having a particle and not having a particle. And it is this electron fractionalization that Mike was talking about. So it's, it's quantum information that is stored globally, that is protected against errors by topology.
Fascinating.
Yeah, I realize that it's a mouthful of nice words.
I know. But how does it look?
So let me bring you back to something practical, something that you can hold in your hands. Because what I've done is actually I have brought one of these electronic devices that we use to study the special properties of these Majorana fermions. And we would actually, Satya, like if you could start thinking about Majoranas on a daily basis, every day. So I hope you accept this Majorana chip and put it at some visible spot in your office. And
you know what? I've been looking forward to this day, the Majorana day. And you said something else. I mean, you said I should keep it but not look at it.
Yes, be very careful because as you know, if you look at a quantum superposition, you destroy it.
That's right. That's why I don't see the cat both dead and alive.
You also want to have the box?
Yeah, thank you. That's pretty awesome. So, Charlie, the fact that, so this seems like a transistor moment to me. Yeah. But obviously we've got to build a computer. So how are we going about scaling this?
Well, I think that's exactly the right metaphor. And I think that because this is a kind of a, abstract and esoteric topic, it's worth remembering that first transistor, you have that picture of the history of the transistor in your head, really didn't become the technology of today until we figured out how to put a lot of them on a chip, and maybe even more importantly, to have one transistor turn another transistor on or off, which of course was a materials development. We had to understand semiconductors in order to be able to use electricity, to switch electricity. But electrons that form the transistor have their own additional tricks. And we've known for 100 years that, for instance, the electrons in an atom don't just buzz around like the planets going around in a solar system, but that they're just a kind of a cloud of probability. But that trick, if you imagine the same kind of extension from the transistor to the chip, if you say, well, I'll take this electron, which isn't anywhere at the same time, and use it to control another electron, which isn't anywhere at the same time, then you have the essential idea of quantum computing. That is, everything is turning itself on and off, but nothing has a state until it's measured. And it seems like a fantastically powerful idea because then everything is on and off at the same time, so there's all of this parallel computing.
And how does the system look, though?
But I think it's important to say, when we start building these things, it's at least Microsoft's belief that this idea may not be enough, this idea of on and off at the same time, because those states are so fragile that as soon as you look at them, like you do with the chip, or you measure them in any way, all of that magic disappears. So instead of doing the original transistor model or the atom model of 100 years ago, that kind of model, which hasn't existed before. I mean, we've had 100 years to get used to quantum mechanics and 100 years to get used to atoms. But we've only had a few years to get used to this electron fractionalization idea.
Right.
So what we need to do then is the same generalization. We need to take these fractionalized electrons and have one of them affect another one and another one, and have a whole chip of each of these fractionalized electrons controlling the state of another one. So these chips are going to get bigger than that, but the same operating principle of the fractionalized electron protected as non-local information, but then turning on and off its neighbors will be the principle of operation. It's important to say, though, that even with this topological protection, room temperature is not going to be enough to have this machine work. It still has to be down at very low temperature. So I think what this machine will look like is something like this box right over here behind us, maybe also up on the screen in a secend. That looks like nothing.
Where is the machine?
Don't look at it.
It's actually
It's
in
there.
a superposition.
That's the quantum joke, I think.
It's there and not there.
That was an excellent joke. Yeah. Okay, so I'll say in words what that thing is going to look like. You did that on purpose.
Yeah, that's right. But why don't you describe it in the slide?
Yeah, so if we just say what this thing is going to look like is the hard engineering part of getting this little chip and its neighbors connected all up is to get that thing down near 0.01 degrees Kelvin where the whole chip can operate. You don't have to worry about Schrodinger's cat being alive or not alive at that point because it's not going to survive at the bottom of one of these dilution refrigerators. But the chips work just fine down there.
Yeah.
And not only do they work fine, but the quantum superpositions continue to be in this superposition state because at those low temperatures, there's no vibrations to do the accidental measurement or nothing happens down there. And all of the, little skinny lines that you see going down are what we need in order to control the vertical lines moving down, and those have to solve this very tricky problem of controlling the chip, but not accidentally measuring it.
So where are we? I mean, there's so much magic here. I mean, you have this cryogenic material. There is all of these, parts that all have to not only new materials, but new physics has to come together to build this out. So where are we on this journey?
Well, I have to say, I think that this is what Microsoft has done that's really unique in its approach to quantum computing, which is to, first of all, recognize that each one of these steps is actually very hard. In fact, it may seem like making the chip with the Majoranas is the hard part, or thinking of the idea is the hard part. But actually, they're all hard. And everything from the software that we'll hear about in a second to the cryogenic engineering is extremely difficult. So where are we? We've invented new materials that support Majoranas. We've built the chips. They're back in our labs in the refrigerator, down at the bottom of the refrigerator with our students and colleagues working hard to check off the list of all of the properties that they're supposed to have, to fractionalize the electrons and verify that they're at the two ends of the chip. And the work is going forward.
That's awesome. That's what explains, I guess, why we have one mathematician but two physicists.
Exactly.
So, Krista, going to computer science, from a computer science system perspective, how does this all look?
Yeah, so in the slide previously, we saw this stack, right? So at Microsoft, we're building this complete stack, a comprehensive full stack solution so that we can actually run revolutionary applications on this really revolutionary device. So this includes the quantum chip that we've just discussed in this dilution refrigerator, but it also includes a cryogenic classical computer that's also operating in the dilution refrigerator. And this is unlike any classical computer we have today, right? It has to operate at 4 Kelvin. That's around minus 452 degrees Fahrenheit. That's pretty darn cold. And we need that to control the quantum computer itself. And then, of course, my favorite part, on top of all of that, you need software. After all, we sit at room temperature. We're not going to be able to jump into this really cold fridge and program the computer from there. We're going to sit out here and have tools that enable us to program the quantum computer. And then, of course, software will be throughout this fridge, enabling the cryogenic computer to control and operate the quantum chip.
That's pretty amazing. So if people in the room, want to get going with the quantum computer and the software stack, what would they do?
Well, at Microsoft, we think about tools and especially software tools. So that's what we're developing for all of you in the audience to get involved. So we're building out a full software stack, and this, I'm really excited, especially about this new programming language we've designed. It's a domain-specific language, and it's designed especially for programming a scalable quantum computer. And so this language, it enables you to write quantum solutions, quantum applications. And then from there, we've integrated it into the tools, a tool I know you love, Satya.
Visual Studio.
Visual Studio. So we've integrated this language into Visual Studio, and with that, we're able to provide quantum debugging support, the ability to visualize a quantum state as it goes through the program. You can syntax, color your code, and it makes it very readable, very understandable, very, digestible. It's tools that you already know and have a feel for. And then on top of that, you can test your algorithms in advance by running them in a simulator. So we're offering both a local simulator that you can run on your laptop, your desktop, that allows you to simulate around 30 qubits for your quantum applications. And then I'm really excited about a state-of-the-art Azure-based simulator that we have that enables you to simulate around 40 qubits in Azure.
That's so awesome. So thank you all so very much. I'm so excited about the progress you're making, the foundational math, physics, and computer science coming together to help us tackle some of the biggest challenges that we still face as a world. Thank you.
Thank you.
Thank you, Christy.
Thanks, Satya.
So I want to close out where I started. At Microsoft, for us, whether it was building the basic interpreter for the Altair, or whether it was building the simulator in Azure for quantum computing, the core soul of our company, the core purpose of our company is to empower every and it has its uses. It definitely does. We all seek to unlock the unimaginable and solve the impossible. Thank you all so very much for being here this week with us at Ignite and Convision. Thank you so much.